Grade 10s. The first lesson on longitudinal waves will follow now. It's the work on page 47 to 52. So first of all, we need to go through some definitions. A longitudinal wave is a wave where the particles of the medium moves parallel to the direction of propagation. So if you have a slinky spring and you're holding a slinky spring in your hand and the slinky spring is lying like this, then the longitudinal wave will be created by a vibration that is going along the same horizontal line. And what the what the disturbance does is it stretches the slinky spring out and it compresses the slinky spring. So a longitudinal wave is a series of compressions, and the parts where the slinky spring is stretched out is called a rarefaction. So if you look at a slinky spring, your disturbance, the vibration causing the disturbance, is parallel to the direction in which the wave moves, and you've got compressions are the regions of high density, and rarefactions are regions of low density. So here are two videos that you can watch to see the generation of longitudinal waves. So compressions are the regions of high density and rarefactions are regions of low density. So compressions, the medium's particles move further, moves closer together, and with the rarefactions, the medium's particles move further apart. And the interesting thing is that sound is propagated through a medium as longitudinal waves. So the vibrations caused by the loudspeaker compresses and rarefacts the air particles or the solid particles or the liquid particles, depending on where you are, and then it causes the eardrum to vibrate with the same frequency. We'll discuss sound waves in more detail in the next chapter. So pause the video to do the questions on the practical activity on page 47 to 48. And here it would be wise to have watched those two videos that I've shown indicated. So to conclude, I just want you to look at the longitudinal wave in this medium. We have the wavelength. Per definition, the wavelength is the distance between two consecutive points in phase, like from the center of a compression to the center of the next compression would be a wavelength, or from the center of a rarefaction to the center of the next rarefaction, that would be a wavelength. Now, if you look at the distance between the center of a compression and the center of a rarefaction, that would represent half a wavelength, and a quarter of the wavelength represents the amplitude of a wave. Now, amplitude is dependent on the density of the compression or the rarefaction. I'm going to describe that on the next slide. So on this slide, I'm showing you how the particles in air is compressed or stretched out, which is called rarefaction, where we are looking at something with a low amplitude, where there is less compression because there is less energy in the disturbance. Whereas if we look at the second wave here, there is a greater amplitude, means that the compressions are more dense, which means that there is more pressure in the wave and therefore more energy. So what is the amplitude's definition? It is the maximum displacement from the rest position. Now with longitudinal waves it's a little bit more complicated, because the amplitude of a longitudinal wave is the measure of how compressed or how rarefied a medium is, which is determined by the pressure in the compression or the separation of the particles in the rarefaction. It's half the distance between the middle of a compression and the middle of a rarefaction, and if you want to say it is a quarter of a wavelength in a longitudinal wave. The next definition I want us to look at is that of the wavelength. It is the same as for a transverse wave. So it is the distance between two consecutive points in phase. Next definition is the period. It's the same as for transverse waves. The time taken to complete one vibration oscillation wave. Next is frequency. Frequency is the inverse of period, so it is the number of waves completed in 1 second. Next is the wave speed. It is the distance the wave travels in 1 second. So the next question is how the longitudinal waves are represented on paper, because it's not always very sensible or easy or quick to represent them as lots of dots pressed together, or as lines close together or lines further apart. So we use an instrument called an oscilloscope, and that transfers the sound waves. Mostly the longitudinal waves we work with is the sound wave. It converts the sound wave into an electric signal, and then it represents the compressions as crests and the rarefactions as troughs on the oscilloscope screen. The next homework you have to do is exercise 4 on page 50, number 1 to 3 and number 6.